Yeah, let's start.
Okay. All right. Good evening, guys. Welcome you all to IGC. So this is going to be a demo class on aerodynamics. So if you guys have any doubts at any point of time, please feel free to unmute and ask, or you can put down in the comment section. Those who are in YouTube, and if you are in live class, you can put down in the chat box. Okay. You need not wait till the end of the class to ask your doubts. If you have anything, just let me know. Okay. All right. So let's get started. So before starting, just a brief intro about me. My name is Sanjay, and I teach aerodynamics and gas dynamics here at IGC. So my background is aerospace engineering. I did masters from IISc Bangalore, and my specialization was aerodynamics. I worked on both experimental and computational aerodynamics, including both low speed and high speed. So yeah, that was about me. We'll get to know more later on. Let's go ahead. So yes, as I said, this is going to be a demo class. So I'll just try to briefly touch upon a topic. At this stage, because we have not started the course, it is just for you to see how the lecture goes. So this is how it is going to be in the live class, in the live classes later on. So it's okay if you are not able to understand everything, but if something you are able to get it, that is good enough. Okay. All right. So what we are going to discuss today is on low speed wind tunnel. Okay. Now, this topic is a little bit far from the theoretical aerodynamics. Okay, so aerodynamics is generally divided into theoretical aerodynamics and theoretical aerodynamics, computational aerodynamics, and experimental aerodynamics. Okay, so in theoretical aerodynamics, we kind of study the theories which are underlying principles of the flow. Okay, in computational aerodynamics, you study the theory and you apply that to the bodies physically, but you kind of code it up. Okay, you take the help of a computer and you try to get the solution which cannot be solved analytically. And then we have experimental aerodynamics, where we do physical experiments and we understand the aerodynamics behind the flow. Okay, so this topic, low speed wind tunnel. Wind tunnel, you all might know already if you are from aero background. If you are from mechanical background, yeah, you might not. At least you must have heard it, but you might not know in detail. So that's what we are going to discuss. So before that, let me just start asking you guys a question. What is aerodynamics? What do you mean by aerodynamics in very layman terms, or however you know? You can put down in comments, or you can speak. What do you think we are going to study in this course? Yeah, anyone? Okay, dealing with fluids flow over certain bodies, study of interaction of air with different bodies, behavior of any object in an air medium. Good. Yeah. So you guys are very close. Uh, yeah. So aerodynamics essentially means it is the study of. Okay, it is the study of flow past bodies. So we are going to study about the flow past bodies. What do I mean by flow past bodies? Is it an internal flow or an external flow? What kind of flow is it? It is going to be a external flow, right? Because flow past bodies means you're going to study about the flow over any surface. okay, surface of the body. Now, it is not that internal flow is not considered in aerodynamics. It is, but most of our applications relevant to aerospace deals with flow over lifting surfaces or lifting bodies, right? Where we are interested in flow past bodies. Okay. So now, what kind of bodies are we talking about here? What kind of bodies do we want to study? Is it any random body, or are we talking about specific type of bodies or very specific kind of bodies? Yeah, anyone? Very good, Aditya. It is streamlined bodies, right? So we are going to talk about something called as aerodynamically designed bodies, okay? Or as he rightly mentioned, these are known as streamlined bodies. Now we will learn what is this so-called streamlined bodies mean. So streamlined bodies, I'll just tell you in very short. So streamlined bodies means these bodies are very carefully designed. The external surface or the shape of the body is so designed such that you minimize your drag. Okay, so drag is a force that is a result of the airflow past a body, which opposes the motion, right? That is drag. We all know why does drag occur. So streamlined bodies are designed to minimize the drag and to maximize the aerodynamic forces. Okay. So we will see how do we design such bodies and what is its relevance in when we go deep into aerodynamics. Okay. So we are going to mostly understand what is the streamlined bodies, how do we design them, what are the physical parameters that influence the flow over streamlined bodies, and variety of things. Okay. So this is about aerodynamics in very, very brief, in just a statement. Okay. All right. Now, so you're going to study about these streamlined bodies. As I said, you can develop some theories around it. You can understand that by writing down equations. Okay, and you can even simulate. So we have something known as CFD, right? What is CFD? Computational fluid dynamics, which is a very powerful tool that is used to um, understand the flow behavior over any body, flow past bodies or flow through bodies, right? In so we have commercial softwares or we have commercial codes that is going to give you the solution, right? Once you simulate the flow over these bodies. So there are variety of ways that you can understand aerodynamics, but what happens is often uh, people don't tend to trust uh, these methods like CFD. Of course, theoretical is something which is developed out of the basic principles, so that we have to trust. But what happens in reality is much far from what happens in theory. Okay, so in reality, things are very different. The assumptions are different. Okay, whereas to derive any theory, we would have put a lot of assumptions. We'll simplify our problem. Okay, but it does not happen in reality. So that is why we need to always do some kind of experiments. Okay, we have to do experiments. Why do we do experiments? It is to validate our theories. It is to validate our CFD codes. Okay, whether what we are doing is correct or not. So experiments means in aerodynamics, you are physically going to understand, you're physically going to see the flow field, and you are physically going to test these bodies uh, to understand the aerodynamics. Okay. Now, uh, when it comes to aerodynamic testing, where do you do that? So we do that in wind tunnel. Okay. So we will understand about wind tunnel. So what is a wind tunnel? Right? A wind tunnel is a device. Okay, it is a closed device, or you can say sometimes it could even be an open device, which is used to test aerodynamic bodies. Okay, uh, not just aerodynamic bodies, you can test any kind of bodies, but most of the applications are relevant to aerospace where we test only aerodynamic bodies. Okay, and we obtain the aerodynamic data out of the testing. What kind of data do you obtain? You obtain data like what are the forces, what are the moments on that body at a particular flow condition. Okay, how about the stability of the body, the performance of the vehicle. So there are a lot of useful data that you generate out of this wind tunnel experiments, which you will later on use in the design phase. Okay, so that is about wind tunnel. So it's a device that is used to physically test the aerodynamic bodies. Okay, all right, we will come to wind tunnel part, but even before that, so as I told you, it is all about the study of flow past bodies. Now, when we say it is a flow, right, it has to satisfy a few governing equations, right? Because any flow satisfies the governing equations. And what are the governing equations that we have, guys? Can anyone tell me? You would have learned governing equations, right, in fluid dynamics? Continuity, okay, momentum, and energy. Very good. Right. So you basically have three governing equations. That is mass conservation, momentum conservation, and energy conservation. Right. So any fluid flow or flow past any body has to satisfy these three governing equations, and it is the solution of this governing equation that gives you the that gives you meaningful results about the flow, right? So ultimately, what do you want? You want the velocity field, or you want the pressure field, or you want the temperature field around the body, right? So that you get by solving these governing equations. So these governing equations are going to form the basis of your uh, theoretical, computational, or experimental analysis, right? But it is mostly in the theory. Okay. So now we will just quickly see this particular equation called as Bernoulli's equation. You guys would have definitely heard about this Bernoulli's equation right from your high school. So again, can someone tell me what is Bernoulli's equation, or what does this equation talk about? Yeah. Relation between static pressure and velocity. Okay. Is it only the relationship between static pressure and velocity? Total energy constant. Okay. Law of conservation of energy. So is it only the law of conservation of energy? Is it or is it also the law of conservation of momentum? Yeah. Momentum as well. Okay, good. All right. So you guys know, right, what is Bernoulli's equation? So Bernoulli's equation tells you that yes, as you guys rightly mentioned, it is law of conservation of energy, but it says that the total mechanical energy of the system remains constant. Here our system is the fluid, right, or the fluid particles. So the total mechanical energy remains constant. So what is there in the mechanical energy? You have different forms of energy like kinetic energy, pressure energy, internal energy, right? Potential energy. So the sum of all these energies, this remains constant. That is the simplest form of Bernoulli's equation that we know, right? And this is what we have learned. But in our course, we will in fact start from deriving these governing equations. Okay. And when we derive, you will understand that this Bernoulli's equation that you see here, it comes from so-called momentum equation. Okay, so we start from the momentum equation, which is Navier-Stokes equation. Okay, from the Navier-Stokes equation, we will put some assumptions. Okay, and we will boil it down to Euler's equation. Okay, Navier-Stokes equation is simplified to Euler's equation. Again, on application of some assumptions, we will come to Bernoulli's equation. Okay. So in fact, Bernoulli's equation is not just saying that your energy is constant, it is also saying that the momentum is conserved. So it is a combined effect of momentum and energy. Okay. So you will later on see that we know Bernoulli's equation is applicable for incompressible flow, right? It is not that we don't have Bernoulli's equation for compressible flow, but it is in a different form, which we call as energy equation for a compressible flow. Okay, that is somewhat different, but it is primarily for an incompressible flow, right? Now, for an incompressible flow, because we don't need energy equation explicitly, because incompressible flows are mostly isothermal flows, the temperature changes are not very significant, so you can neglect the energy equation, but rather club it up with momentum equation and you get this Bernoulli's equation. Okay, so what does Bernoulli's equation say? It says that P by rho plus V squared by 2 plus Gz is constant. Now here the notations, they carry the usual meanings. Okay, P is the pressure, rho is the density, V is the velocity, G is the gravity, and Z is the elevation. So basically it is telling you P by rho. P by rho is the pressure head, right? This is the pressure head. V square by 2 is the kinetic head. It is kinetic energy per unit, um, per unit. Uh, what is it? P by rho is, so you are dividing the entire thing by the length, right? By uh, by the length. So you get the head, right? So it is pressure head, kinetic head, and Gz is the elevation head. So these heads, they remain constant. Sum of these head, or the sum of the total energy, remains constant. Okay. All right. So this is the Bernoulli's equation that we know, and as one of you mentioned, it is a relationship between static pressure and velocity. So yes, this is the only equation that gives you the relationship, direct relationship between pressure and velocity, static pressure and velocity. Okay. All right. So this is the Bernoulli's equation that you see here. Okay. Now, you can see here down, I have written the same Bernoulli's equation, but in a different form. Can someone tell me what is the difference between the first way of writing and the second way? So we have written the same Bernoulli's equation in two different forms. If someone can tell me what is the difference, is it the same or is there any difference? Do you think it is the same? Instances considered. Okay. So what are the instances, Rishwant? All right. So it's okay if you do not know at this point. We will come to this when we actually derive the Bernoulli's equation. But Bernoulli's equation is not applicable to any type of flow. Okay, that is not the case. So we know that it is applicable only to an incompressible flow. That is the very first assumption. The second assumption is, on top of the flow being incompressible, okay, on top of the flow being, one second. So on top of the flow being incompressible, we additionally put an assumption that the flow is also irrotational. Okay. Now, what do you mean by an irrotational flow? An irrotational flow means uh, the fluid elements, they do not rotate about their mean position or about their axis. So there is no there is a deformation, but they do not rotate. So they are the fluid particles are irrotational in nature. Okay. And what is the consequence of this? It's a very beautiful concept, and it's a very powerful assumption saying that the fluid is irrotational. We will come to that later on. But for you, it is just to say that mathematically, the curl of the velocity vector vanishes. That is meant by irrotational flow. Okay. Now, when you say that the fluid is irrotational and it is incompressible and also it is steady, you can apply Bernoulli's equation at any 2 points. Okay. You can apply Bernoulli's equation at any 2 points in a irrotational flow. So that is the second form. Okay, where you have applied it at point 1 and at point 2, and the things in the bracket is the same. Okay, so you can apply it between any 2 points. This is one case. The other cases, let's say if the what if the flow is not irrotational but it is still incompressible, so you can apply, but you can only apply it along a streamline. So the first case, the first form of Bernoulli's equation is applicable only along a streamline. Okay. Now what is a streamline? A streamline is the path of the flow, right? We will formally define that later, but streamline is the path of the flow. So you pick a streamline, it is applicable at any 2 points on that streamline, okay, but not across the streamlines if the flow is not irrotational. But if it is irrotational, then you can apply it between any 2 points. So I just wanted to highlight this difference of Bernoulli's equation because why you will understand later. Okay, and you have to be very careful when we say Bernoulli's equation is applicable or not applicable, in which cases, right? So that engineering judgment is very important. Okay, all right. Now, so this is a Bernoulli's equation. It talks about relationship between pressure, velocity, and all. Now, where is it used? What is the application of this? So there are various applications relevant to us. We have applications like Venturi meter, low speed wind tunnel, and pitot probe. So we will study these three major applications of Bernoulli's equation. Now, what is Venturi meter? Venturi meter is a device. It's a small device like this. It is used to measure the airflow at any point. Okay, it is a flow measuring device. It measures the flow rate at any given point in the flow. Okay. Now there are disadvantages to Venturi meter as well. It is not always efficient. Okay, but for our physical testing of aerodynamic devices or aerodynamic objects, we use low speed wind tunnel, right? So we are going to learn about wind tunnel. What is it and how is Bernoulli's equation actually applied in the wind tunnel? Okay. All right. So far, any doubts, guys? Any doubts? Anyone? Is it clear? Is it clear, guys? Any doubts? Okay. All right. So we'll move on. Now, we can classify the wind tunnels in different types. So first, based on the air speed. So what is the speed of the air through the wind tunnel? Okay. And in what regime is that speed classified as? So based on the air speed, you can classify the wind tunnel as low speed wind tunnel or high speed wind tunnel. Okay. Now, what is that clear demarcation between low speed and high speed? So generally, low speed wind tunnels they simulate incompressible flow. Okay? They simulate incompressible flow. So we say that the flow is incompressible in a low speed wind tunnel. When it comes to high speed wind tunnel, it deals with supersonic flow or hypersonic flow. So this is mostly for flows beyond Mach 1. Okay, so this can give you flows beyond Mach 1 or it can be a supersonic flow. We have supersonic wind tunnels or blow down wind tunnels. We also have hypersonic wind tunnels where the flow free stream velocity can become hypersonic, where the Mach number can go beyond 5. Okay, so we also have wind tunnels which can simulate hypersonic flows and they are known as shock tunnels. Okay, they are also wind tunnels, but basically they use a different principle, so they are known as shock tunnels which can simulate hypersonic flow. Okay, and why did I use a word called as blow down wind tunnel over here? Blow down wind tunnel, it has a separate mechanism. I will explain you later. That is the reason it is known as blow down wind tunnel, and this type of wind tunnels can only give rise to very high speed flows. Okay, like a supersonic flow or a hypersonic flow. You also have blow down wind tunnel in a low speed. It can give you low speed as well, but the fact that you are blowing down the air from a highly compressed chamber of air, you will take the advantage of that to obtain high velocities in the test section. Okay, so that is why we use blow down tunnel, and based on the direction of the airflow. So depending on how the airflow takes place through the tunnel, you can classify it as open circuit wind tunnel and closed circuit wind tunnel. So again, I will explain in the further slides what do you mean by open circuit and closed circuit. Okay. And based on the test section, you can classify it as open test section or closed test section. Now, generally, most of the wind tunnels that you see have closed test section, right? Closed test section means you have physical walls in the test section, and the model is kept inside, and then you simulate the flow. You turn on the flow. Okay, so the model is not experiencing; it is not affected by the atmospheric conditions. It is it is experiencing the actual flow conditions. But when it comes to open test section, the test section walls are not there. It is physically open. So you keep your model there and it experiences the atmospheric conditions or the ambient conditions. So this type of wind tunnel can be used when you want to test your models with ambient conditions. Okay. If you want ambient conditions, you can use open test section wind tunnel. Otherwise, we mostly go with closed test section wind tunnels. Okay. So Sharon has a doubt in wind tunnels. Technician test with airfoils or prototype of a wing. Yes. So as I mentioned, wind tunnel is basically a flow testing device. Okay. So you test different models. It could be aerodynamic surfaces. It could be models of your flight. Okay. You can use scaled down version of your aircraft. You can test that. If your wind tunnel is so big, if the test section is so big, you can even put in the full scale model and test. Okay, you can test aerofoils, you can test turbine blades, compressor blades, propeller blades. So any lifting surface or any surface for that matter which gives you some sort of aerodynamics. To test its performance, you will always use wind tunnel. Okay. Okay, Sharon, got it. All right. So now let's understand more about open circuit wind tunnel. Okay. So you can see here, this is the schematic of a typical wind tunnel. When I say typical wind tunnel, it is mostly open circuit wind tunnel. So you can see that it is a very long device. It is not a short device like venturimeter that it can be inserted anywhere. So it typically occupies a lot of space, and sometimes the space has to be chosen very carefully to capture the proper flow conditions inside. So it occupies a huge space. So you can see here, it is basically a duct. Okay, the wind tunnel is basically a duct. What type of duct is it? Is it a straight duct? No, it is a variable area duct. Okay, it is a variable area duct. So you can see that initially there is a inlet of the wind tunnel. Okay, there's an inlet from where the air gets in. The air is captured through the inlet, and there is a converging section. Okay, there is a convergent duct which converges, and then you see there's a constant area duct again, and then again there is a diverging duct or a diffuser, and again there's a constant area duct. Okay, and then you have a fan and a motor here. All right, so let's slowly understand why this construction and what is the relevance of each part. So this wind tunnel is basically run by the so-called fan, which is mounted at the rear of the wind tunnel. If you guys have you guys seen wind tunnel, low speed wind tunnel in your college? If you guys have anyone, low speed or high speed wind tunnels, at least aero guys must have seen, I guess. Yeah, good. So, did you notice there's a fan at the rear? The fan runs and it sucks in the air. Yeah. Have you guys noticed there's a fan? Yes. Okay, good. So, there is a fan which runs at a fixed RPM. It is not a fixed RPM. You can change that RPM using the motor. So, you can change the RPM of the motor. It will run the fan at that particular RPM. And that is what makes the tunnel to absorb the flow from the surrounding. Okay, so what does this tunnel, what happens here is the technician will fix a particular RPM, and generally the fan RPM or the motor RPM rather, you can say, it is a function of the velocity in the test section. Okay, I will tell you how. Okay, so generally we fix the fan RPM and you switch on the tunnel. The moment you switch on the tunnel, not at the same instant, but after some time, once a steady flow is established, you will see that you are getting the flow of that particular velocity in the test section. Okay, so you have the inlet. At the inlet, you would have seen it is a bell shaped of inlet. Okay, it is a bell shaped inlet. It is not a very sharp inlet, it's a bell shaped inlet. Why is there a bell shaped inlet? It helps to grab the flow, it helps to absorb the flow. Okay, so once the flow is taken in, it is the concept of capture area. We have something known as capture area. You will learn that later on. So capture area is an invisible or it's a hypothetical area which is formed just upstream of your physical inlet, okay, which captures the air and passes it to the inlet. So this bell-shaped portion of the inlet acts as a capture area. Okay, here it is not a hypothetical area; it's a physical area. Okay, so the air is taken inside. Once the air is taken inside, it passes through something known as settling chamber. What is the settling chamber? The settling chamber, so the air, the atmospheric air has a lot of turbulence. It has a lot of eddies. What do you mean by eddies? So the air is all like circular motion, right? It has a lot of uh, vortices, eddies, and rotational effects. It is not really a very straight, streamlined air. Okay, it might be a turbulent air. So what happens is the settling chamber helps to reduce these eddies. It will cut off the eddies. Okay, so for that purpose we have something known as wire mesh inside the settling chamber. Okay, what do we have? We have wire mesh. So the wire mesh kind of removes the eddies, so it will make the air it will kind of make the turbulent air into straight. Okay, it will straighten the streamlines. Instead of the eddies, it will straighten it. So that is a function of the wire mesh which is inside the settling chamber. Okay, now for this purpose, if you look at the tunnel from outside, you will see that it has a peculiar type of structure. We call it as honeycomb mesh. Okay, so you will see this type of hexagonal structure. It is a net of this hexagonal shaped structure. Have you seen this type of structure when you look the tunnel from outside? Yeah, guys, have you seen this type of, yeah, yeah. So this is known as hexagonal or honeycomb structure or honeycomb mesh. Okay, honeycomb mesh. So what does this honeycomb mesh do is that it when the air passes through this honeycomb mesh, because it has a lot of edges and vertices, okay, it is going to cut down these eddies, or it is going to remove these rotational effects from that air, turbulent air. Okay, so once it passes through the hexagonal or the honeycomb mesh, it is going to be almost straight to the axis. It is going to be aligned to the axis of the tunnel. Okay, now instead of honeycomb mesh, you can also have circular meshes like this. Okay, and some tunnels also have just square meshes. Okay, but what is the advantage of using honeycomb mesh is that it has 6 edges, right? So because more edges, it is more efficient in cutting down the eddies, removing the eddies. Okay, so once the air passes through that, now the air is being taken from the atmosphere. So the air that enters is with the ambient condition. Okay, atmospheric condition. So it will have certain atmospheric pressure, it will have certain velocity. Now the velocity is not zero initially, it is fairly low, very very low, but it is not zero. If it is zero, then you cannot have the flow, right? So there will be a minimal velocity, and there is an inlet area which is A1. Okay, so this V1, P1, A1, rho1, T1, these are all the inlet conditions of the air. Okay, now what happens when once the air is reached end of settling chamber? So settling chamber is a constant area section, so nothing changes the property of the air. But we don't want that velocity in the test section, So test section is where we test the models. So there we want to mimic the flow conditions, right? So we want a different flow condition. So how do you change the property of the flow? You either keep a varying area duct, okay, or you do some external work done on the flow, or you do some heat transfer. But we are not getting into that. Okay, we will not do any heat transfer or work done, but we will give a variable area duct. Now, what type of variable area duct will you provide? You will give a convergent duct. So for an incompressible flow or for a low speed flow, a convergent duct acts like a nozzle. What do you mean by nozzle? Nozzle will accelerate the flow. Okay. So the flow that enters with the velocity v1 exits this nozzle with a velocity v2. Okay. And v2 is going to be higher than v1 because it is a nozzle, it is going to accelerate the flow. Okay. In wind tunnel terminology, sometimes this nozzle is known as effuser. Okay, it is known as effuser. So diffuser is what diverges the flow, effuser is what converges the flow. So it is effuser. Okay. So what this nozzle is going to do, it is going to increase the velocity. So it is going to expand the flow. Once the flow is at the exit of the nozzle, the flow velocity is very high. Not very high, it is high enough to achieve the flow conditions that you want. Okay, so you would have fixed the fan RPM, right? So that fan RPM or the fan will create equivalent pressure difference, and that will be converted to the appropriate velocity in the test section. Then you have this constant area duct called as test section. It is the most important part of the tunnel. This is the part where you place your models or you mount your models. So in the test section, you have provision to mount your model. There are fixtures, there are stands, okay, where you can suspend your model or you can place your model. You can rigidly fix it. You can do whatever. Okay, there are different provisions inside the test section. So it is generally a rectangular based section. It could be even be a circular cross section. It can be a cross section of different shapes. Okay, but in low speed tunnel, generally owing to the space, we'll have a rectangular kind of test section. Now you will place your model. What is a model? Model is what you want to test. Let's say find out I want to find out how much is the lift generated by wings of an aircraft. So what I will do, I will just either I will place only that wing or I will place the aircraft. Now, can I place the entire aircraft in my tunnel? No, obviously no, right? So what I'll do, I'll scale the aircraft down. I'll scale it down. I'll make a smaller model by using the principles of dynamic similarity. Okay, we will see what is dynamic similarity later on, or you can take it as your homework to understand. But you will use that principle of dynamic similarity to scale it down. You make a smaller model and you place it inside the tunnel. Okay, you mount it in the test section. Once you mount in the test section, you switch on the tunnel, you will get the desired flow, the velocity that you want. And because because there is a nozzle here, the velocity has increased, the pressure has dropped. Okay, you know from Bernoulli's equation what happens, right? Pressure decreases, velocity increases. And remember, test section is an area which has constant cross section area. So the cross sectional area does not change, which means the properties at the inlet of the test section is same as the property at the exit of the test section. Without the model I'm talking about, okay? Without the model. If you place the model, then there will be flow over the model. It will change the properties downstream. So because it is a constant area test section, you will have at every station, you will see that the properties are the same. It's a uniform flow. But once you place your model inside and the flow takes place over the model, it will disturb the flow physics. It will disturb the streamlines. It will change the nature of the flow. There can be wake, there can be eddies, there can be flow separations. Okay. There can be a lot of phenomena that can happen, which will change the nature of the flow downstream. Okay. But the idea of keeping the test section as constant area is that you don't want to you just want to capture the flow physics. Okay, the flow should not be disturbed because of the structure of the tunnel. Now, what happens? So here you have the higher velocity at the exit of the tunnel, which is V2, and then you provide a diverging duct. You provide the diffuser. What does diffuser do? Diffuser is going to convert your kinetic energy to pressure energy. So once your kinetic energy is converted to pressure energy, the velocity is converted to static pressure. So if you see at the exit of the diffuser, the velocity V2 is now V3, with V3 being lesser than V2 and P3 higher than P2. Okay. So basically you had first accelerated the flow. You will use that in the test section to test your model. You will again decelerate the flow back to its original velocity or even lower, and you will dump it to the atmosphere. You will dump it to the atmosphere. Because you are dumping it to the atmosphere, you see the circuit is always open. So every time this tunnel runs, it is going to make use of new air, fresh air from the atmosphere. It is going to run over the model, it is going to throw it to the atmosphere. So every time the circuit is open, right, it is not closing. That is why it is known as open circuit wind tunnel. That is why it is open circuit wind tunnel. So the air that is taken is used inside the tunnel and then it is dumped into the atmosphere. Okay. So you can see at the exit, you will have ambient conditions because it is a subsonic flow. Subsonic flow cannot withstand any pressure difference. So you have ambient conditions at the exit. And there is a fan at the rear which runs continuously to create the pressure difference for the flow. Okay. So this is about, so there is lot more about to talk about the tunnel, but this is just for your understanding, and we will look into it in detail later on. Okay. So is this clear to everyone? Any doubts here? Very good question, Rishwant. So you have the fan at the end of the tunnel, right? See, okay, Rishwant, I will come to your question a little bit later when we do an analysis. Okay, you will understand that better. I'll keep you on hold. Okay, we will come to it. Yeah. Others? Any doubts? Okay. So now let's see what is a closed circuit wind tunnel. So the closed circuit wind tunnel is very similar to the open circuit tunnel. The only thing is you close the circuit. That is, you connect the front and the rear of the tunnel through through a through another mechanism. So what happens here is you have a reservoir. Okay. Here also you have the settling chamber, which is known as a reservoir. Okay. And the air is taken through the inlet of the tunnel. Air is taken through the inlet of the tunnel. Okay. But remember here, the difference is every time the air that is used by the tunnel is not the ambient air. Okay. It is not the ambient air. It is the air which is circulated inside the tunnel. Air goes inside the tunnel, everything is same. Nozzle, test section, diffuser, everything is same. When it exits out of the diffuser, it is not thrown to the atmosphere, rather it is circulated inside the tunnel. It is circulated inside the tunnel. What do I mean it is circulated? When the air is passing like this, it will come, it will turn. So you have to turn the flow. Now the flow does not turn automatically. You have to give a provision. So we have something known as turning vanes. Okay. We have something known as turning vanes. It will turn the flow. And what is a turning vane? Turning vane is basically, it is like a series of airfoil sections here. Okay. It is like a series of airfoil sections which will turn the flow. Why do you give airfoil sections? That is to minimize the pressure loss. Otherwise, you will have a significant pressure loss. And once you have a pressure loss, the total energy spent or the power required to drive the tunnel becomes very huge. Okay. So to minimize the pressure loss, you keep some streamlined bodies as a turning vane, and then you turn the flow. And there's a fan here which again does the same job in open circuit. It will give the pressure difference, so the flow will keep on circulating. Okay. So what happens is the same air keeps on circulating all the time. Okay. And the same air is used to test the model. Okay, so you can see from the construction of the closed circuit tunnel that it occupies much more space compared to open circuit. Right? Open circuit is just one duct, one huge duct, but here it will occupy the entire room, right? So the cost of maintenance and operation is much more complicated when it comes to closed circuit tunnel. Okay, uh, but can you tell me one advantage of the closed circuit tunnel? Why is this? Why is this construction important? What happens when the same air circulates every time through the tunnel? Can someone tell me? Less wastage of energy. See, there is wastage of energy because not really wastage, but you have to power the fan, right? The fan has to run. It is not going. The tunnel is not going to run without the fan. So, which is there in open circuit as well, closed circuit as well. But yes, the power requirements will be more in case of closed circuit tunnel. But yeah, what advantage do you see here in terms of the quality of the flow? Avoid turbulent flow, that you can avoid even in open circuit because you have settling chamber. Here also you have settling chamber, right? You have honeycomb meshes which can remove the eddies. You can do that. What else? What else do you see? Higher efficiency. What efficiency do you mean? Are you talking about aerodynamic efficiency? Aerodynamic efficiency is by the design of the model. It is not the property of the tunnel. Okay. So you can see that because the same air is circulating every time through the tunnel, the flow conditions or the ambient conditions are not going to change. Very good, Vijay. Yes, the result is reliable, which means the quality of the flow that enters the tunnel is the same every time, more or less. There is not much difference, right? What happens in the case of open circuit tunnel? In the case of an open circuit tunnel, you can see every time new air enters the tunnel. So if the ambient, let's say if it's a summer season, you will have a very hot air where the density is less. If it is a winter season, you will have a very cold air, ambient air, where the temperature is less, the density is higher. So it is going to affect the quality, right? But in the case of your closed circuit, there is no change in the quality of the air that enters the tunnel. So every time the same air that is circulating, so the changes in ambient conditions is less. So the mimicking of the flow in the test section becomes perfect. Okay? So you get that desired conditions. Okay. Whereas every time in open circuit tunnel, you have to calibrate it to the current ambient condition. So that is an advantage of a closed circuit tunnel. There are other advantages as well. But the only thing is, it is somewhat, the mechanism is complex and the flow has to turn. So there's a pressure loss, all that. Okay. All right. So I hope the difference between open circuit and closed circuit is now clear. Now let's do some analysis. Okay. So yeah, we will assume a quasi 1D flow. Quasi 1D flow means the flow properties only depend. So if you take a duct, if you take a variable area duct, the flow properties only depend on the uh, direction, only depend on the x direction. They do not depend on y direction, or they do not vary along the cross section, which means if the pressure over here is P1, at the entire cross section the pressure is only P1. The pressure is not changing in the across the cross section. Okay, but it will change when you move from this station to the next station. Here it is P1, here it will become P2, here it will become P3. Okay, but this P3 is going to be P3 all along this cross section. So that is known as quasi steady flow or quasi one dimensional flow. So where you kind of have no changes across the cross section. Okay, So you can assume the flow to be one dimensional if you have a quasi-steady assumption. Okay, so we'll assume the flow is one dimensional. We will learn more about it when we come to this later on. So let's say you take this case only, take the case of this open circuit tunnel. Okay, so you have settling chamber, you have the nozzle, you have the test section, and you have the diffuser, and then there's a fan. Okay, so you see that here the velocity is v1. Okay, area is a1. At the exit of the settling chamber, velocity is again v1, area is a1. Then it passes through the nozzle. Exit of the nozzle, the velocity is v2, area is a2. Exit of the test section, because it is a constant area duct, again velocity is v2, area is a2. Exit of the diffuser, velocity is v3, area is a3. Similarly, the pressure, okay, here it is p1, p1, p2, p2, p3. So let's derive some relations. So you can apply continuity equation across the nozzle to get the velocity in the test section, right? If you apply the continuity equation, so this, you can see that this is a control volume here. So it is a single inlet, single outlet control volume. If you apply the mass conservation, you will get A1 V1 is equal to A2 V2. Okay. So from here you see that V2 is going to be A1 V1 by A2. A1 is known to us, A2 is known to us, that is from the construction of the tunnel. V1 is the inlet velocity. Okay, that is also known to us. Okay, so you get V2 from here. Once you get V2, similarly, you can say for the diffuser, same mass conservation, you get A2 V2 is equal to A3 V3. From here, you will get V3. Okay, that is the velocity at the exit of the diffuser. And you can relate the pressure to velocity through Bernoulli's equation. So you can apply Bernoulli's equation along the axis of the tunnel. Now again, see guys, we are writing the equation. It is not about blindly writing down the equation. It is about understanding the assumptions. So here, what are the assumptions? So you are assuming the flow is steady. If the flow is unsteady, you cannot write any of these equations. Okay. So the first assumption is that the flow is steady. Second assumption is that the flow is incompressible. It is only when it is incompressible this form of continuity equation is valid, and this form of Bernoulli's equation is valid. Third assumption is that the flow is uniform. If the flow is not uniform, or I mentioned the quasi 1D assumption. Okay, it's a quasi 1D flow. If the flow is not quasi 1D, then again the way you apply mass conservation is not the same. Okay, and you also assume that that there are no body forces. Okay, that there are no body forces. So you are neglecting the gravity. You see in the Bernoulli's equation, the GH term, the gravity term is neglected. That is also because you are considering it at the same height. So you take the axis of the tunnel and then you apply this equation at the axis. So the height is the same. But even otherwise, if you want to apply Bernoulli's equation between any 2 points, you can say that the height is almost negligible. Okay. But again, remember here, this is always along a streamline. Along a streamline. Why along a streamline? Because you don't know whether the flow is irrotational or rotational. So if it is either the case, along a streamline is always better. Okay. So you can say P1 plus half rho V1 square is equal to P2 plus half rho V2 square is equal to P3 plus half rho V3 square. Now you relate the velocity through area. Okay. You can just carry forward this derivation and you can express the velocity V2, which is the test section velocity, as a function of the pressure difference P1 minus P2 and the ratio of the areas A2 by A1 and density rho. Because it is an incompressible flow, the density is constant. Okay, so you will take the rho term out, and A2 by A1. A2 by A1 is the ratio of the areas across nozzle. It is sometimes known as contraction ratio. Okay, it is known as contraction ratio, which is A2 by A1. Sometimes it is referred to as small n. Okay, so then you can write this as n square. Okay, so contraction ratio is the ratio of the exit area to the inlet area of the nozzle. So you can see you have now eliminated V1, that is the inlet velocity that we don't know. But A2 by A1 we know, rho we know. What we don't know is now P1 minus P2. We don't know how much is the pressure drop across the nozzle required to accelerate the flow. So can someone suggest how do you experimentally measure this pressure difference? How will you measure this pressure difference experimentally? Very good. It is through manometer, right? So you will use a YouTube manometer that can be connected to, so you have the nozzle. Okay, so you use a YouTube manometer. Okay, this is connected to the inlet and the exit of the nozzle. You have the flow. So you will have the difference in the level of mercury or whatever the fluid, manometric fluid that you use. So that difference is, let's say, delta H. And there's a specific weight of the fluid, which is gamma. Then you can say that between these 2 points, that is 1 and 2, P1 minus P2 is going to be gamma into delta H. Right? Gamma is basically rho G. Rho G into delta H. This rho is not the rho of air, it is rho of the manometric fluid. So you can find the pressure drop using the manometer. You can connect a manometer and find out. Once you know that, substitute it back into the equation. So now you can see all the terms over here can actually be measured physically. Delta H is the height difference in the manometer, which you can measure. Gamma is the property of the fluid that we know. Rho is the density of the air that we know. It is incompressible. You know the ambient conditions. A2 by A1 is the contraction ratio that again we know by the dimensions of the tunnel. Okay, so using this, you get the test section velocity, which is important. So you know if I'm placing my aircraft model in the test section, what is the velocity that the aircraft model is experiencing? Okay, or what is the flight velocity, V2, that you will know. Okay, so once you know V2, you can find out P2 using Bernoulli's equation, right? You again apply Bernoulli's equation, P1 plus half rho 1 V1 square is equal to P2 plus half rho V2 square. Because you know P1, P2, you know, because you know P1 minus P2 and you know your V2, you can always find out P2. Okay. So you will know what is the pressure difference between the inlet and the test section. Now, and you also know this is equal to P3 plus half rho V3 square. Okay. So now, let's say the inlet area of my tunnel. I'll come back to this slide so that you can. Yeah. Here, let's say the inlet area A1 is equal to the exit area of the diffuser, which is A3. Then can I say V1 is equal to V3 by continuity equation? Okay. And then again by using Bernoulli's equation, can I say P1 is equal to P3? If my P1 is equal to P3, that means the inlet pressure is equal to the exit pressure of the diffuser or the pressure at the exit of the tunnel. If this condition is true, do you think there will be a flow through the tunnel? Do you think there will be a flow through the tunnel? No. Why? Because we need some sort of pressure difference for a flow to happen, right? A flow cannot happen without a pressure difference. So if P1 is equal to P3, then you will never have a pressure difference. But this is in theory. In reality, this is not true. In reality, P1 is never going to be equal to P3. In fact, P3 will always be less than P1. Why so? Because you know this is a flow through duct. And because there is a flow through duct, the flow is passing through this wind tunnel, it will encounter a lot of obstacles. So what are the obstacles? You can have friction. We did not consider friction in our analysis. So the flow is not really inviscid. It is a viscous flow. Okay. Air has at least some viscosity, right? So it is not really inviscid. So you have friction. Okay. So you have one-dimensional flow with friction, which we call it as a Fano flow. Okay. Fano flow is one-dimensional flow with friction. So you see in Fano flow, what happens when a flow passes through a straight duct with friction, the pressure reduces. Okay. It can be a subsonic flow or a supersonic flow. If it is a subsonic flow, the pressure decreases. If it's a supersonic flow, the pressure increases. Okay. So here it is a subsonic flow. So P3 is always going to be less than P1. There is going to be boundary layer on the walls of the tunnel. Because of the boundary layer, there are going to be losses, flow losses, right? So finally, the flow that you get at the exit is not really going to be of the same quality of the flow that you started at the inlet. Okay? That is the reason. That is the reason, Mr. Rishwant, you asked, why do you need a fan at the exit? Did you get your answer now? Because if you don't keep the fan, you are never going to get that so enough pressure difference to have the flow. Okay. What did you say about it being invisible? So see, I will come to that point in our classes, Danesh. But air is there is a viscosity of air, right? It is very less. You can assume it to be inviscid, but there is some viscosity, and that viscous effects becomes dominant close to the walls of the tunnel. So if you see the test section, when the air passes through the test section, you can see that there is a boundary layer growth. Okay. So because of this, there will be a drag on the walls. There is a friction, right? So you will have losses. The total pressure will be reduced. Okay. So although it can be considered as inviscid, but not close to the walls at least. Okay. Does it answer your question, Danesh and Rishwant? So you can think about it. What can happen if you don't have a fan? Okay. If you don't have a fan, do you think you will get enough pressure difference so that the um, flow can be absorbed? No. See, the fan is used to create a suction pressure, right? The suction pressure you want to create at the end. So you need a favorable pressure gradient, right, for the flow to happen. If it is an adverse pressure gradient, you will not have a forward flow. You will have a reverse flow. So if you place the fan at the beginning, uh, how is it that you are going to create that pressure difference? See, you can have the fan at the inlet, which is for an aircraft engine. There you want to compress the flow, right? You want to compress the flow with the pressure. So there you have an gradient in the compressor. But here, if you keep the fan at the entrance, then it is going to compress the flow, and it is very difficult to pass the flow through the test section, through the tunnel, because there is not enough pressure difference. Okay. So to create a suction pressure, you always need the fan at the end. Right? Okay. So I hope that answers your question. So now, yeah, so this is all about the story of tunnel. Let's quickly see a question and then we can wind it up. All right. So here you see there's a question. A low speed wind tunnel has a contraction ratio of 14:1. So what is this 14:1, guys? This is A2 by A1. Sorry, this is A1 by A2. 14:1 is A1 by A2 because A1 is always higher than A2, right? So it is A1 by A2, which is 14:1. Cross sectional area is 1 meter square. So A1 of the test section. So of the test section, it is A2, right? So A2 is 1 meter square. So your A1 is going to be 14 meter square, right? and the static pressure difference between the settling chamber and the test section is 40 centimeter of water column. So the delta H is 40 centimeter, which is zero point 0.4 meters. Okay. Assuming G is 9.8, the density of air is constant 1.2, density of water is given to you. What is the speed of air in the test section? Can you guys find out? Can you calculate and let me know the answer? We have just seen the formula, right? How to calculate the speed of the air in the test section. Please do that and let me know what is the answer that you get. It's the same formula that you have to use. Okay. V2 is equal to root of 2 times P1 minus P2 by rho times 1 minus A2 by A1 square. P1 minus P2 can be written as rho GH, rho G delta H. So what is the answer that you are getting? So guys, whenever you get a question, the first step is always to write down the data. Okay. Write down what are the data given to you in the question. Then here you can draw the schematic of a wind tunnel quickly to note down the stations. And then you start applying the equations. Okay. And you are not expected to remember this formula. Okay. You can always derive this. You can use continuity equation, Bernoulli's equation, derive it. It's just 2 steps. But so in aerodynamics, I don't expect you guys to remember most of the lengthy formulae. Okay. That is not the idea. You can always derive it, but there are few formulae that you cannot derive it on the spot. So which you should remember. But you should always know the concept. Okay. Yes. Anyone? What is the speed that you are getting? Did anyone calculate? Yes, guys. Make sure to convert all the units properly. $74.2. Okay. Others? Others also getting the same answer? What about others? Punit, Vishwant, Shravani, Vijay, Yash, 81. Okay. So Vishwant is getting 81. So 81 seems to be the right answer. Okay. 81.03 meters per second. You can check your calculations, Aditya. Okay. So yeah, so this is a numerical answer type question where you are supposed to type the value. So they will tell you whether to type it in correct to 1 decimal places or 2 decimal places, or write integer, you can appropriately type. Okay. So I hope this was clear to you guys. Any doubts? Any doubts about the wind tunnel operation, or how did we do this problem, or anything? So this is all about low speed wind tunnel. The high speed wind tunnel runs on a different philosophy. Okay. All right. So that's all. If there are no doubts, uh, thank you guys. So we just stop presenting. Yeah, I'm done, sir.
Yeah, thank you. So anyone have any doubt, guys? Who all are in this session? Anyone have any doubt? Okay, no, right? And those who are watching this session on YouTube, guys, you guys can further contact us for further course details and other things. Okay, and batch is starting from April 22nd. Thank you, guys.
Okay, thank you guys.